Can you hear me? Okay, great. Yes, thank you. So in today's session, I'm going to be talking about Bayesian inference, and it should actually be in brackets for non-statisticians. I think Bayesian inference is something that's well established. Yeah, let me maybe go to my, let me just, okay. Yeah, so Bayesian inference has been established quite a long time ago. Of course, there were some developments. In between that, in the 1970s, there were some developments with Metropolis Hastings. In 1987, physicists proposed a hybrid Monte Carlo approach. There were some software developments in bugs, open bugs, stand PyMC3 that allow the rapid development and application of Bayesian inference technologies. The no-Newton sampler has been proposed in 2014, and it has also been used in the different software packages. And the big thing is that Bayesian inference has become a universal language to many fields. Just by looking at the publications, you would often see non-statisticians having to use Bayesian inference to solve the problems. And the reason for that is we have models. I think all fields have some sort of model that we need to use and to calibrate. And we have limited data available, but we still need to make decisions using that limited data. And so the purpose of this talk is going to be to give you an intuitive overview of the Bayesian inference process that will allow you to understand the principles that is behind that. And I'm going to use linear regression as a vehicle for that. I think all of you have performed linear regression before. Okay, so let's get started. So we would like to model the following data with this model. So equation 1 is the model we would like to fit to the data. And on that slide, I'm showing 10,000 data points with an x value between 0 and 1. So we would like to know what the two parameters are, theta 0 and theta 1 for this data set. I think if you had to take a guess by looking at this data, you would most likely guess that theta 0 should be equal to 1. That's going to be our y-intercept. And the gradient of this line is going to be most likely 3 if we just draw a line through that. So because we have a lot of data points, intuitively we can see the line that would go through that data. It's not very difficult to see that. So we would guess that this line is a line that fits it quite well. If we want to formalize this a bit, we can say let's identify some loss function that we want to calculate. And in this case, I'm going to minimize the sum of squares error, which is a very common loss function in modeling. If we minimize the mean squared error in this case, we would get the line with theta 0 equal to 1 and the gradient equal to 3. So it matches our intuition. If we now limit the data and we say we have 5 data points, we still get a general sense of the trend of the data, but now it becomes a bit more difficult to get the optimal parameters for this data set. If we had to draw a line, if I had to give out a piece of paper and everyone had to draw their own line through it, there would be some variations between different people because we have limited data, the data has noise added to it. If we want to again formalize this process and we say we want to have the optimal model that presents this, and our loss function is the mean squared error function, we can then get a line that looks like this. And in this case, the intercept is not exactly, it's not close to 1, to be honest, and the gradient is maybe a bit closer to 1, to 3. So because we have limited data, in this case, the loss function helps us to find an optimal model. But this model differs quite significantly from the model with many data points. So you could see that there's some variation in the data. I think it's maybe much clearer in the previous picture that there's noise added to the measurement. So each time that we perform an experiment, we generate data, there's new noise added to it, and the data looks different. From a very far away, it looks the same, but each individual data point will change. So because we have this inherent randomness added to the data, we need to ask the question, how will this impact the model we are fitting to the data? So if we had to re-perform the experiment with 5 data points and the underlying model remains exactly the same, but because of measurement noise, there's some randomness, how would this line change? So what I did was I took this model that I showed you now, I added a variable epsilon, and this epsilon is a zero mean random variable. That's the noise component. And I made theta 0 equal to 1 and theta 1 equal to 3. So it's exactly the same as that initial model. But now we're going to generate a number of data points. We're going to fit a model to it. We're going to regenerate the data points, fit another model to it. And we're just going to see how the models look like if we repeat the number of experiments. Okay, so just to show the process, on the left side is that initial data that I showed. And on the right side, I generate 100 experiments of 10,000 data points. So of course, you cannot see the exact detail there, but you can at least see there are many experiments there. So we have many data points on that right slide, or the right side of the slide, and we're going to fit a line through that data for each case. So if we fit a line to the one data set, we have one line. We repeat that for the 100 cases, so we have 100 lines we're going to fit through. But we can see just from looking at this plot, we have 10,000 data points for each experiment, and the data looks essentially the same. Of course, if you look at each data point, there's some variation, but there's no ambiguity how that line is going to look like. If we fit the sum of squared error to that function, we get essentially one line out. There are 100 lines, but we get one line out from that, because each model that we get from the experiment looks exactly the same. So we have enough data in this case to obtain the model. So we only need to perform one experiment to get the exact line, the underlying model for us. So there are no observable differences between the different lines of the different experiments. If we redo this experiment for the five data points. So on the left are the original 5 data points. On the right, I generated 5 data points 100 times, and I just added a bit of noise on the x-axis just to show the distribution of the data points. So again, we have 5 data points, we fit a line to it, we generate a new 5 data points, we fit another line to it, and we repeat that process 100 times. And from this, we can see we obtain clearly many models from this data set. So even though the underlying model was exactly the same, because we have limited data and we have noise added to it, we are recovering different, let's say, models from this data set. So the randomness in the data and the limited data that we have makes us uncertain what the actual model is. So there's some variation, even though the parameters were exactly the same. And this is a common situation. Of course, we have in some applications, we have this big data phenomenon where we have a lot of data and we need to make this work. But there are also some applications, and this is typically the applications I work in, we have very limited data. The data are very expensive, and we still need to make decisions based on that. And so we are uncertain now what the exact model is in this case. And so we still need to be able to make decisions from one experiment. We don't have a luxury to repeat an experiment 100 times necessarily. Okay, so there are two classical inference procedures that can be followed. The first one is the frequentist perspective to inference, and the second one is the Bayesian perspective. So in the frequentist perspective, to fit models, so we can use a frequentist perspective to fit a model to that data. So a frequentist perspective is probabilities are viewed as frequencies of a specific outcome. So if you had to flip a coin 100 times, you use that frequency of the number of heads to give you a statement on probabilities. And a classical and the most common or practical frequentist approach is maximum likelihood approaches. Okay. You might have heard that term before. And what a frequentist approach does is we try to fit a maximum likelihood estimator to the data, but we use those estimators. So we use sampling distributions and confidence intervals to make statements using those estimators. I'm not going to go into detail there. I'm just trying to leverage some things you might have heard in the past. If you had done introductory statistics course, you undoubtedly encountered confidence intervals. Sampling distributions might have been implicit, but you would have also encountered that. With the Bayesian perspective, the probabilities are directly seen as quantifications of uncertainty. And the parameters that we try to infer, or the parameters of the model, are described using probability distributions. And this allows us to have a natural framework for uncertainty quantification. I'm not going to go into detail between the different perspectives of Bayesian and frequentist. You can find a good discussion in the textbook by Bishop that's freely available. There's also a textbook on uncertainty quantification that also goes into detail on the differences and the benefits, etc. But before we can do Bayesian inference, we first need to revisit some probability distribution theory. So I'm going to just do a brief introduction or just review of that, and then we will move over to Bayesian inference. So we're going to look at two probability distributions. The one is a Bernoulli distribution, and the second one is a Gaussian distribution. Okay, so with a Bernoulli distribution, we are essentially modeling a binary process with a binary outcome. So if you think of a coin flip, it can either be heads or it can be tails. So if I flip the coin, it lands on heads on some cases and it lands on tails the other cases. If the coin is, let's say, loaded, or let's say it prefers one side above the other, then you would, let's say it's more inclined to land on heads, then the proportion of heads would be higher. So, but because the fact that each time that we flip it, the outcome is different, we need to use that probability distribution to describe that behavior. So a Bernoulli distribution is an example of a distribution that can be used to describe that behavior. So the probability that, so this is the probability distribution. We have X, which is heads or tails, so it's a discrete representation, and we have an underlying parameter theta. So theta is, if you had to look, if we think about it in a frequentist perspective, if you had to repeat an infinite number of experiments, how many of them would be heads and how many of them would be tails? So theta is the proportion of heads that we would expect. So the probability of encountering heads, so X is equal to 1, is theta, and tails is 1 minus theta. So if I had to simulate an experiment, if I had to draw samples from this Bernoulli distribution, for theta is equal to 0.1, so in this case, it actually is going to land the whole time on tails, so you would use this coin if you want to make a bet against somebody and there's some money involved. So then you're going to choose tails most likely. The 0.51 is an even, or it's a fair coin, so it's going to prefer heads and tails equally. And we can see that, so for the theta is equal to 0.1, we had 10 heads, and so the number of ones was 0.1 out of 100. So 0.1%, 10% of the 100 throws. So that matches exactly. For theta is equal to 0.5, we had 49 heads and therefore 51 tails, but it's close to 0.5. I think the important concept that you need to take away from this is each time that we repeat any random process, the outcome of that process is going to be different. And even though the parameters were exactly the same, the viewed parameters or the observed parameters might be different. We already saw that with the linear regression case, even though that underlying model was the same, we saw different slopes and intercepts for that same underlying model, because the view we get from the data set, we have limited data available. So if I make theta is equal to 0.2 in this case, we would see in some cases we would get exactly 20% of the time times heads, but in some cases it might be 26%, in some cases 19%, in some cases 22%. So each experiment looks different. If we go and plot a histogram of the proportion, or the, let's say the number of heads in this case, we can see that if theta is equal to 0.1, we would have many cases where we have, let's say, a value of 0.1, but we also can encounter a value of 0.2. If we took 100 coin flips, we will, for one case, we might have a case where we had 20 heads. Even though the coin has a preference for 10% of the times, we might observe 20% because of the randomness in the data. If we make it 0.7%, 70%, it looks like this, for example, but we might observe a 55% or even an 85% proportion of it. So the important takeaway from this is, if we have limited data, we are inherently uncertain. Okay. If we now move to a continuous space where we have a Gaussian distribution, so now it's a probability distribution function over some x or some random variable. A Gaussian is parameterized by a mean and by a standard deviation or variance. So sigma is the standard deviation, sigma squared is the variance. So we have two parameters that control the behavior of this distribution. This is the mathematical representation of it. You might have seen this before, but the probability distribution looks like this on the screen for different parameters. The important thing to take note is, because to be a valid probability distribution, if we integrate it over its full domain, the integral should be equal to 1. So it means that if we start to change the scaling of the distribution, if we increase the variance, the height needs to decrease to ensure that the integral is equal to 1. So we can move the distribution around. So the red curve has a mean of -2. The blue curve has a mean of 0, and the purple curve has a mean of 2. And the variance of this curve here is the largest, so it's 1.5 squared. Okay, so this is a Gaussian PDF. Okay, so another distribution is a cumulative distribution function. So that happens if we integrate it from the one domain to the other, from the negative infinity up to some value x, and it's a cumulative distribution of that plot. So this is a way also to view the probabilities of the Gaussian random variable. So we can use this plot to ask the question, what is the probability that we will observe a value of x smaller than a number? So the probability that x is smaller than 10 is 100%. The probability that x is smaller than -8 is 0% for all free models. Here, it will be different for the free models depending on the shift. So this is if we want to calculate probabilities. Okay. This is a probability distribution, so we can sample from the distribution. So we can generate data with this distribution. So if we sample from it, if I generate 10,000 samples, the samples for one distribution might look something like this. So it's just completely random. If we go and plot a histogram of those samples, the histogram of the samples would look like this, and I superimposed the PDF of that distribution. So that's the relationship between the samples and the histogram and the PDF. If we go and change the parameters of this distribution, in this case, it has shifted up and we've decreased the standard deviation or the variance, then this distribution would look like this. So we can see here again, because we decrease the variance, the height of the PDF increases. This is an important concept we'll touch again on a bit later. Okay, so just in summary, we have a PDF that looks like this, and this is going to be our model. Our models are going to look like this that we're going to try and fit to the data. So this is the PDF. If we generate many data points from this PDF, it looks like this, the samples, but ultimately if we take many samples from this distribution and we plot the histogram, we recover the original PDF. So the histogram of the samples are equal to that. Okay. So if I take one sample from that distribution, and I need to predict what the mean of that distribution is. So if let's say I have 10, or let's say one data point from the distribution, I need to predict the mean. I can only use that one data point to predict it, and so the best guess I would have would just be that value, that exact data point. So you can imagine that if we had to use only one data point to predict the mean of that distribution, the variance would be quite large. The one sample might be 3, the other sample might be -2, and so we would have a significant variation in the mean. If we have 100,000 data points and we calculate the mean of that distribution, then if we generate another 100,000 data points, that mean will remain exactly the same. So the moment, it's again that concept of the moment we have limited data, the more uncertain we become. And so just to reiterate that point, if I take 100 data points, I generate, so I perform an experiment, I generate 100 data points from that distribution. So on this curve, I show 5 experiments. So each experiment contains a new realization of that process, and it contains 100 data points in it. If I calculate the mean of those 100 data points, they would be different. So even though the PDF remains exactly the same of that distribution, the means would vary, and if we plot the distribution of the means, we would see it looks something like this. So we might observe most frequently a mean of -2, but in some cases the mean might be -1.5, and in some cases it might be -2.5. And it's the same if we calculate the variance of that distribution. So the moment that we calculate quantities, or we fit a model to random data and we have limited data, there's going to be some variation if we have to repeat that experiment. And we need to be aware of that when building models. So if I give you a single data set and you need to make decisions based on that, you are going to be uncertain unless you have 100,000 measurements and it's a simple process. So we need to be able to quantify the uncertainty. So now we're going to, now that we have established the probability distribution let's say, just revisited that, we can go back to linear regression. So in this, I'm now going to introduce the concept of maximum likelihood and Bayesian. And yeah, so we'll incrementally get to the full Bayesian inference problem. Okay, so let's revisit the following data set. We again would like to fit a model with two unknown parameters. Okay, so this is a mistake here. This theta 0 plus theta 1 is the mean of the model. It's a copy and paste error. But so we would like to fit equation 15 to the data. We have theta 0 and theta 1. Those are two unknown parameters. And we acknowledge the fact that there's some randomness in the data. So we make it explicit by adding a random variable plus epsilon. So each time we generate an experiment using that model, theta 0 remains the same, theta 1 remains the same, x remains the same. But there's this epsilon that can either translate the data up or down. So, and we make it explicit in this formulation. We have a random variable present. Okay, so we have a model form, but there are an infinite number of parameters we can choose. So, which of the following models are most likely for the data? So, I specifically use the word likely here. So if you had to choose one of the three, which one would you choose to be the most likely? Maybe it's just just to get some feedback. If you had to choose model 1, let's say the one in the left corner here, we would think that that's the most likely. Model 2, not. Model 3, okay. So it seems like most people would prefer model 4, most likely, the white space. But so model 1 got the most votes. Okay, so you have an intuition from these 5 data points that there are some models that are better than others. But we need to be able to formulate that in the context of a stochastic model. So I'm only showing the mean of that model, so that means theta 0 plus theta 1. X, I'm only showing that. I'm not showing the epsilon part or the standard deviation due to that. So we would like to be able to, we need to be able to quantify which models are better or not using some method. And we're going to use the likelihood function to do that. Okay. So this model here, if I assume epsilon is Gaussian, so that means if I generate 10,000 data points from epsilon, and I plot a histogram of only epsilon, the histogram of epsilon would look something like this. I'm just going to go back just to remind you. Well, let's maybe make it just 100. If I had to generate 100 samples from epsilon, the distribution would look something like that, or it would be a variation of that. We only have 100 samples. So that's epsilon. But then we also have theta 0 plus theta 1 x we're adding to it. So if we had to write this model in a statistical sense, we can say that we are uncertain what the value of y is. But we know what the mean of this distribution is. The mean of this distribution is this part here. So I just forgot the x there. So the mean of the distribution is this part here. Okay? So it's always going to be that all the curves we're going to generate are going to be centered around that point. They are just going to shift up or down a bit. Okay. Due to that epsilon there. So that's the mean of our distribution, and this epsilon makes us uncertain of that. And that uncertainty is Gaussian in this case. So we can go and describe y as a Gaussian distribution. Okay, so we can go and say, for a given x, that we select, we can simulate data from this distribution by sampling from a Gaussian with a mean equal to theta 0 plus theta 1x and a standard deviation equal to sigma squared, where this is the standard deviation of, or the variance of the noise, not the standard deviation. So this is the model form we are assuming. Okay, so maybe just, I think this is an important concept. Is there something I should repeat before I continue? Is there a question maybe here? Or is this,
Why do we take theta 0 plus theta 1x to be the
Okay. So it's a good question. So if I take that model, I'm just going to use the board here. If I take, I'm not so sure which one it is. Okay. So if we look at that model, okay, so I'm going to select theta 0 plus theta 1x. I'm going to select theta 0 equal to 1 and theta 1 equal to 3 in this case. Okay, so let's just draw that line. If x is equal to 0, y is equal to 1. The slope is equal to 3. So when x is equal to 1, that value will be equal to 4. Okay, so that is just that one part of it. Okay. Now we're going to generate, now we're going to add noise to it. So we're just going to add, so we generate 5 data points. I'm going to try and equally space 5 data points again. So we only have 5 data points for each experiment. So actually we can remove this part here. Okay. Each experiment we are performing, we add new noise to it. So for each data point we add noise, but each time that we repeat it, we add new noise. It's random. Okay. But we're adding noise that is a mean of 0. So if I plot the distribution of epsilon, it will be centered at 0. Okay. So if I go and just added this data point, at one data point I add noise. In some cases it's going to be here, but so I sample this value, but in other cases it's going to be there. So if we plot that, we'll see that the distribution would look Gaussian. So the mean is centered at the model's prediction, but we're adding some randomness in between. And it's the same for the next data and the next one. So if I look at this one here, that model always predicts that point. Theta 0 plus theta 1x is always equal to that value if these are the parameters. But each time that I generate new data from that, the one point might be there, the other point might be there, the other point might be there. And on average, they're going to cancel out. Okay. So again, it will be Gaussian if we could repeat it in infinite number. The spread of these data points are governed by sigma squared, or sigma is proportionate. So if we look at the one extreme, we will make sigma equal to 0. If we make it so, the variance so small, then it's going to be a deterministic model. If we make sigma very large, it's just going to be always look randomness. We're not going to see the underlying model structure. So sigma squared just controls that spread of that randomness. Okay. So this concept clear. I think if you understand this concept, then the rest of it is going to be much easier. Great. Thank you. Is it the top one or the?
I think you can leave it on actually. It doesn't.
Okay. Great. Okay. So we have that model now. It's Gaussian with a mean equal to sigma 0 plus sigma 1x, and we have a variance equal to sigma squared. We now need to calculate the likelihood of this model. We need to have some loss function that we want to let's say, to minimize. But we first need to be able to evaluate what is the likelihood of the model for a single data point before we can talk about a data set. Okay, so what we're going to do is, so we have one data point at x is equal to 0. Our model predicts this line here if we make theta 0 equal to 1 and theta 1 equal to 3. So it predicts that line. We observe this point here. If we repeated the experiment, the point would be at a different place. But we observe that point there. So what we're going to do is we can plot the PDF of this distribution over y. It's exactly what I actually did here on the board. This distribution was over y for a given x. And if we change the x value, this distribution might shift up or shift down, depending on how the model looks like. But so we can plot the PDF of this model, and we can compare this PDF of this model that is centered around the mean of the model. So the mean at x is equal to 0 is equal to 1. So if I make x equals to 0, the y value is equal to 1. And I can go and calculate the height of this PDF. So you can see here, if I only had one data point, and I had to move this PDF around, and I wanted to make it the best representation of that data point, I would center that PDF at the data point, right? It will have the highest height at that point. So it's the best score that we can have. I don't want to have this PDF at a location where the data point is somewhere here. You can see that that makes intuitively sense. It doesn't match that case. So we use the height of the PDF as a measure of, let's say, how well it fits this data point. I'm not sure if I skipped now 2 slides. Okay, now. So this is exactly a concept I'm explaining here. So this model is actually centered at that y value of equal to 1. Because x is equal to 0, this term vanishes, this term vanishes. So theta 0 is equal to 1, so we center that PDF at 1. Okay, we have the data point there, and we go now to, and we calculate the height of that PDF at that data point. So the height of the PDF quantifies to us the likelihood of the model with these parameters for this data point. So how likely is this model for this data point? So we have 5 data points, and we looked at 3 models previously. 2 of them looked very similar, and the one was just a horizontal line. So let's look at the likelihood of the parameters for those 5 data points. So for model 1, our prediction looked like this. And we can see here, if I go and plot a PDF at this point here for this data point, the distribution of that PDF looks like this. It's centered at 1. And we can actually see for this model and for this these 5 data points here, this point is located somewhere at the tails. So this model doesn't predict that data point very well. But if we look at the next data point, it's exactly at the center or close enough to the center. So the model predicts this data point very well. For the third data point, we can see it's slightly to the left of the model. Our model is over predicting that data point. So we can see that's also represented by that PDF. And we can continue for the 4th and 5th data points also. Okay, I'm just going to do it for the second model also. So for the second model, we can see that that first data point is not predicted well at all. That data point, according to the PDF we currently have, is somewhere far from the distribution. So that's not a good representation. This data point is much better. This one is exactly at the center, so this one we're predicting very well, but the other ones we're also predicting very poorly. So we can already see here that the heights of the PDF will indicate to us which models are better when we compare them. Okay, I'm not going to repeat this for the third model. The process remains exactly the same. Okay, so now we need a way to quantify this. So we mentioned we can use the height of the PDF. So we have a model. That model places a PDF at each x that we want to evaluate. We have demonstrated this a bit earlier. So if we have a model, we choose theta 0 and theta 1. Okay, so I chose it equal to 1 and 3 for the case on the board and also on the slide. So if I choose that model, I can go and evaluate how well this model fits. So I can go and place PDFs there that this model predicts, and I can see how the data compares with respect to that. So we use the heights of the PDFs, and we can use the likelihood function, which just calculates the product of the heights. So what we're doing is we're saying, what is this height here? Let's multiply that height with that height, with that height, with that height, and with that height. And that is the likelihood function. We can also go and calculate the log likelihood. If we calculate the logarithm of this, so the log of this is equal to the sum of the log of the Gaussians. So we can go and sum the log of the heights if we want. And actually, so I'm not really going to necessarily emphasize this as strongly in this presentation, but equation 20 is much better to use because of numerical precision issues. If you're multiplying 100 numbers with one another and all of them are smaller than 1, at one point you're going to struggle with numerical precision, where the log is much more stable. But the principle remains exactly the same. If I'm calculating the product of numbers or I'm summing the log of the numbers, it's going to still indicate to me the same thing. And that thing it's indicating in this case is how well does this model describe the data we observe. The product makes sense because if I have a PDF and that PDF is 0 at the data point we're observing, then that model is not a good fit at all. If our model says this data point can never be seen, then this model is not a good fit, even though it might fit the other data points very well. So we calculate the product of the heights. The height is 0, that whole product is 0. So that model is a poor fit. So we need a model that can fit all of the data as well as possible. Not perfectly well, because then it leads to overfitting, but as good as we can. Okay, so just to further illustrate this process, so the log likelihood or the likelihood calculation process is we have a model, we go and calculate the height of the PDFs for that model at each data point. Okay, so these are the heights. So you can see at this height here is the height for this model with theta 0 and theta 1 equal to these values. At x is equal to 0. The y value we have observed is this value here. So it's that y value there. And we can see that the height is equal to 0.021. So it matches that. You can see that this height here is 1.19. So if we calculate the log of the heights, these are the natural logarithm of the heights, and we can just sum them. So this quantity here is the log likelihood of this model for the given data. Yeah. It can also be greater than 1. So it's not, so because this is a probability distribution, the heights are not interpreted as probabilities. So it's the integral of that. So if I just quickly explain it on the board, I always use this. So if I have a PDF, in this case, this PDF explains to me on the x-axis, the x-axis indicates all of the outcomes we can potentially observe. The height here indicates to us the likelihood of those outcomes. So here at the center, if I had to take a guess, I would guess the mean. That's the best guess I can take. I'm not going to guess at the tails. Okay. So this indicates that to me. But because it's a continuous number, one way to think about that, if we, the probability, if I had to give you, if I had to give you one guess, right, to choose a number here, the probability of that guess would be equal to 0. What I mean with that is, I can guess the value 1. I can guess the value 1.0, 1.000, and I can 1.0001. So there's an infinite precision we can realize into this system. What we're actually asking with this PDF is, what's the probability of observing two numbers or a number in between a range? The probability of observing a number somewhere between here and here is going to be 1. The probability of observing a number between here and here is going to be the area under this. It's going to be 0, or close to 0. So it's not the heights that are the probabilities, but it's the area under the curve between two limits that indicate the probabilities. So the thing that always remains true is the integral under the PDF is equal to 1. So if I give another example, just as a last exercise. If I have a PDF that looks like this, it's uniform between two numbers, and these two numbers are 1 and 2. Okay. The height of this PDF needs to be equal to 1 to be a valid probability distribution. The integral, the area under this curve needs to be equal to 1. So this makes sense. If I take this exact same distribution, but I indicate that the value, or I would have just been simpler just to do this. If I say that this is between 1 and 1.5, this height now needs to increase to ensure that the area under the curve remains equal to 1. Okay, so the integrals that integrate to 1, not the heights. So the heights can be larger than 1. Okay, thank you. So just to reiterate again, just to emphasize, so we get a scalar number out, which is the log likelihood of the model for the given parameters we selected for the data we have observed. So it indicates to us how well does this model describe the data. That's it in short. It's a scalar value. It's the log of the sum of the heights, or the sum of the log of the heights, or it's a product of the heights. So what we can go and do for this exact linear regression model, we have two parameters. We can go and evaluate the log likelihood for any combination of parameters. The process would remain exactly the same. We choose two parameters. The moment that we choose two parameters, we have a line. The moment that we have a line, we have a PDF that we can put at each data point. The moment that we have a PDF, we can go and calculate heights. With those heights, we calculate the heights of the data points, we calculate the product of the heights. Then we have a scale. So we can do this for each combination of data points. And if we do that, we obtain a curve that looks like this. So this is the log likelihood of the model for this data set. And these are different combinations of parameters. To make this a bit more intuitive for you, what I did was I sampled different data points, or different points on this curve, just to illustrate to you how these models look like. Okay, so just to clarify, that didn't include color bars. There are color bars here. Yellow indicates higher likelihoods, that means better fits. Lower value, blue means poorer fits. So ideally, we want to have a curve here in the yellow region. We want to have a model somewhere here. But let's just sample somewhere in the blue region, the green region, and in the yellow region, just to make this a bit more concrete. So if we sample a data point here, or a model here, so the model's theta 0 is close to -5 here, and its theta 1 is also close to -5. So what it means is its intercept is -5, and its slope is negative -5. So this model predicts this behavior. Intuitively, you can see that this is a very bad fit. This is not even a consideration for this data set. And that is because, that's why it is dark blue in this case. It's a poor fit. So if we had to draw, I'm just going to do this, I always lose the things when I am in front, but okay. I'm not going to demonstrate it now. But if we had to have that line, then we placed PDFs on that line, just like we did earlier on the board. You would see that all of those heights would be 0, or very close to 0. Of course, a Gaussian has a continuous support, and that means it theoretically can generate any number, but the most likely numbers are, let me just make this, sorry, let me just do this quickly. So what I'm trying to say is, the height of the PDF here, for all intents and purposes, are 0. The height is 0 in this case. If we take the logarithm of this, we would see that it might be -50,000. So numerically it's 0, but on a logarithmic scale, it's non-zero, because a Gaussian has infinite support. So if I go and calculate the height of this PDF, or the height of the PDF at each one of these data points, numerically it will be equal to 0. Okay? But we can see the log likelihood is -2,000. So that's an extremely small number. That is essentially 0 for all practical purposes. But so that just highlights again how poor this fit is. If we start to move in this yellow region, we can see that the log likelihood improves. Even though the models are still very poor, but if you had to choose between -2,000 and -1,000 on a logarithmic scale, is at least an incremental improvement. So we can sample different regions here, and we can see that as we move towards the yellow region, the models become better. It's still very poor. I mean, a log likelihood of -97 is very small, but we can use that to compare different models. So if I had to choose between this model here and this model here, even though both of them are poor, the one is a bit better than the other one. And we can use the log likelihood as a way to quantify that. If we sample from the yellow region, we can see that the fits look like this. So I just took, I think, 50 samples from this region here. So to reiterate again, this space here indicates to us how well the model parameters at a specific point describe the data. So here the model parameters describe it not very well at all. Here it describes it very well. Okay, so we can use this log likelihood representation to evaluate that. The log likelihood lives in the parameter space. Okay, so we plot it over the unknown parameters we're trying to infer or estimate. If we really want to select the best model, we can go and calculate the combination of parameters that have the highest log likelihood value. And that value is referred to as the maximum likelihood. Okay, so this is one kind of estimator that's used in frequentist statistics. But we need to use the log or we have to use the log likelihood to perform Bayesian inference. So this is an important concept. But just to combine things that you might have seen before, the maximum likelihood is exactly that point there. It's the height of the mountain. So, and afterwards we can use, if we were interested in frequentist statistics, we can go and calculate confidence intervals around the data points. We can perform hypothesis tests if we want to, by making some assumptions about the underlying distribution. But that's outside the scope of this work. Okay. So in the next slide, I'm just quickly going to briefly show you what Bayesian inference is going to do for us. But then again, we need to unpack new things. So then I'm first going to unpack those things on different examples, and then we're going to end with this linear regression example. Okay. So we have a log likelihood plot. That is over all of our unknown parameters. In this case, we have 2 unknown parameters, so we can visualize this on a 2-dimensional space. If we had 10 unknown parameters, it would be a 10-dimensional space. We would have to plot if we wanted to visualize it. Okay. So what we're going to do in Bayesian inference, I'm going to explain this very or in detail after this, so don't worry too much about this now. But what we're going to try and do is, we're going to try and combine the likelihood function. So this is going to be the likelihood function and another function we're going to refer to as the prior to infer a distribution over the unknown parameters. So we're going to try and quantify the uncertainty. We don't want a single model. We're not interested in an estimate. We want a distribution of models. And the distribution of models are going to indicate to us the uncertainty in it. We have one data set available, and we saw earlier for that one data set, if we repeated that data set, each time that we repeat it, we have different models we're fitting to the data, even though the underlying model was the same. So we want to be able to quantify that uncertainty, and this Bayesian inference is the mechanism we're going to use to do that. So for this exact same data set, if I perform Bayesian inference, I can sample from that distribution and obtain all of these models using a single data set. Okay, so for a single data set, I can obtain as many models as I want to. But all of these models are centered around the best value. So what I'm trying to say is, on the left slide, what we did was we generated many experiments. We fitted a model to each one of those experiments, and we saw a variation of models because the data were random and we had limited data points. Using a single data set, we can use Bayesian inference to return that uncertainty. So we can quantify that uncertainty. Because we have limited samples, any one of these models might be a possibility. Some of them are better than others maybe, but all of these can potentially be the underlying process. And that's the concept you need to take away from this. So in Bayesian inference, we don't obtain a single model, we obtain a distribution of models. And we use that to quantify the uncertainty. So I don't want to know what the weather or the temperature is tomorrow. I would rather want to know the temperature is going to be 30 degrees, but it might be between 25 and 35. Then I know how to plan. Or is it going to be between 29 and 32 degrees? So it's much better if we have a sense of that uncertainty. So the weather apps can benefit from Bayesian inference to help us with our planning. But before we can do that, we need to understand what Bayes' rule is. So I already showed you Bayes' rule, but I want to make it as intuitive as possible. So we want to understand what this rule means. Then we want to understand how we can use this to infer unknown parameters. And I'm going to then demonstrate this on 2 examples. So I'm going to explain Bayes' rule now in detail, but are there any questions before I continue? I just want to check. There will also time for questions afterwards, but if there's something unclear, yes?
What if the noise was distribution?
Yeah, so this is another aspect. So when you're modeling any kind of model, you need to make assumptions. Okay, so in this case, I'm making an assumption it's Gaussian. I generated the data, so I also know it's Gaussian. But in practice, we do not know that. So either we need to go and test whether the Gaussian model is good. So Bayesian has natural ways to compare different distributions, for example, using the model evidence. But that is something you still are going to encounter. Is this the correct model form? Is the parameterization correct? Is the distribution correct? But at least the framework I'm presenting here allows you to compare different distributions. And so as the modeler, you still have to make that decision or apply a Bayesian inference in such a way that you can select the most, the best representation. Okay. Yes.
So is it like formal distribution, like discrete distribution?
So yeah, so if you have a discrete or a continuous distribution, then it will depend on the kind of data. So you'd have to first look at that. So you won't confuse a continuous and a discrete distribution necessarily.
So I think we can't do like quadrant distribution because we are dealing with continuous value.
Yes, but I just talked about the example, let's say Gaussian or Laplace. Both of them are continuous. Both of them are symmetric. But if you generate enough samples from that, their PDFs look different. So you still have to then ask the question, is Gaussian the right assumption here? And so the explanation I gave would still be applicable. So yeah, it's correct. You would not confuse the discrete and continuous case, but my explanation was more aligned with just two distribution types. Yeah. Yeah. Thank you. Okay, so let's unpack Bayes' rule. We're going to use this extensively. I'm going to now jump to a different kind of example. So we have two identical urns. Okay, we only see the two urns, but I also have a representation of the contents of the two urns. Okay, so the left urn has 8 red squares and 2 blue circles. The right urn has 6 blue circles, 1 green triangle, and 3 squares. And this is going to be a representation of or explaining what Bayes' rule tries to do on a very basic level. Then we're going to increase the complexity until we can do that. So these are the two urns, and now we're properly mixing them. They have the same number of stones, and we're going to assume the probability of selecting any stone, a single stone, is equal. It's properly mixed. It's not that there are only blue stones on the top. We are properly shaking them. So now we have a few questions we need to answer regarding these two urns. So if we select urn 1, so if we select this urn with the contents shown here, what's the probability of selecting a red stone? If we selected urn 2, what's the probability of selecting a red stone? For urn 1, what's the probability of selecting a green stone? For urn 2, a probability of selecting a green stone. And just the question, what's the probability if I perform this experiment, I sampled 1 stone, what's the probability that it's red? Okay. Okay, so let's make a table in this case. And let's just count the number of stones. I've already summarized that, but now it's a bit more formalized. Okay, so for the first question, we're going to ask, what's the probability of selecting a red square from urn 1? So we know it's urn 1. We know the contents of urn 1. We just want to know what's the probability of selecting that. Any person would like to answer this? Yes? 8 over 10. Yes. So we have 8 red squares we can select. We have 2 blue ones. And so we would expect, if we can select any of the stones with an equal probability, that we can select the red squares with a probability of 8 over 10, 80%. For urn 1, what's the probability of selecting a green stone? you can say with certainty it's 0. We cannot select the green stone from urn 1. Okay, so it's 0. For urn 2, you can follow a similar process. The probability of selecting a red square is 3 out of 10. So the probability that the stone is equal to a red square, given the fact that we've selected urn 1. So we know we've selected urn 2, so this is what this notation means. We've selected urn 2, what's the probability of selecting a red square? So it's 3 over 10. For the green stone, it's 1 over 10. It's very unlikely. We only have 1 green stone in urn 2, so it's not probable. Okay, now if we ask the question, what's the probability of selecting a red stone? We don't care about the specific urn. We took an urn, we sampled the stone from it. What's the probability that it's red? So what we can do here is we can just count how many stones there are and how many of them are red. If we can select each stone with an equal probability, then we would expect it to be proportional to the number of red stones we have in total. So we have 8 red stones here, we have 3 red stones here, so we have 11 red stones out of 20. So the probability is 11 out of 20. Okay, but now we're going to ask a different question. Now we have an urn, one of them, they're not clearly labeled. I give them to you, you sample one from it, and now you just sample a red stone. What is the probability that this urn was urn 1? How would you solve this? Does anybody have an answer for this? What's the probability that the stone, that urn 1 was sampled? So this is just now the inverse problem, yes? Okay, yes. But we can even go a bit, we can start a bit simpler than Bayes' rule. We can again look at the numbers. So let's just look at, we know the evidence. Given the red square we've selected, we know that we are either working with urn 1 or urn 2. Okay. So there are 11 red squares we can select. 8 of them are in urn 1, 3 of them are in urn 2. So the probability that this sample came from urn 1 is 8 over 11. So we have 11 that we can select. Urn 1 is 8 of them. So it's 8 over 11. Maybe just to make this a bit more concrete, let's choose the green triangle. So we sample the green triangle. What's the probability that we sample from urn 1? Yes, exactly. Urn 1 doesn't have a green triangle, so it's impossible that we sample the green stone from. So, oh, this is a mistake. So this is a typo. Urn 2 should be 100%. Okay, so equation 30 is a typo. Sorry. So from urn 1, it is 0%. We cannot sample from a green stone from urn 1, but urn 2 has 1 green stone. So if we selected a green stone, we know immediately this was urn 2. Okay. So this is a mistake in equation 30, and we can see this from the table. So 0 out of 1, this one is 1 out of 1. Okay. There was a suggestion that we can use Bayes' rule for this. Before we do that, we just need to first understand what Bayes' rule is. So if we look at the product rule of probabilities, we can decompose a joint distribution over 2 random variables A and B. We can decompose it as the probability of A given B times the probability of B equals to the probability of B given A times the probability of A. We can rearrange these terms to find an equation that looks like this, which is Bayes' rule. So Bayes' rule in the case was the probability of A given B is equal to the probability of B given A times the probability of A times divided by the probability of B. And we're going to extensively use this. The denominator contains the probability of B. And I should have, yeah. So it contains the probability of B. How we can calculate that probability, in this case, I'm just going to demonstrate this for probability of A. So probability of A is equal to the sum over all outcomes, summing the joint distribution over all potential B's. So that's going to give us the marginal distribution. Okay, so let's formally solve this problem. So if we again ask that question, we've sampled the red square, what is the probability that the stone came from urn 1? So what we're asking is, given the fact that we've sampled the red stone, what is the probability that the urn we selected is urn 1? And we can use Bayes' rule to unpack that. That's equal to the probability that the stone was equal to the red stone given urn 1 times the probability of urn 1 divided by the probability that the stone is red. Okay. So the probability of selecting an urn is equal, it's equal for these two cases. So there have an equal number of stones, so the probability of selecting a specific urn is 50%. If we ask the question, what's the probability of selecting a red stone given urn 1? We've already answered that. It's 8/10. With 8 stones that are red in urn 1, and urn 1 has 10 stones, so it's 8/10. The last thing we need to calculate for Bayes' rule is the probability that the stone is equal to red. And so what we're going to do is we're going to sum that joint distribution of the stone being red and the urns. We're going to sum it over all possible urns. So this is what we're doing here. So the probability that the stone is equal to red, given we've selected urn 1, times the probability that we've selected urn 1, plus the probability of the stone being red if we selected urn 2, times the probability of selecting urn 2. So that's the probability of selecting a red stone. And we can see that if we plug in the numbers, it's 11/20. It again matches our previous intuitive calculation we did. So if we go and substitute these numbers in, so Bayes' rule again is shown in equation 41. If we go and substitute those numbers in, we can see the probability of the stone being red, given we've selected urn 1, is 8/10. The probability of urn 1 is 1/2. The probability of the stone that we selected, a red stone, is 11/20. And if we then simplify this, we can see it's 8/11. So it again matches our intuition or the exercise we did earlier. So this is the basic workings of Bayes' rule. So we ultimately want to get to a place where we can perform this for linear regression. So we need to move to a space where we're talking about parameters. So in this case, I'm going to show you a simple example that explains this process. I've selected functions to demonstrate the multiplication process. This is not for a specific model. I'll explain that now. So this is just going to intuitively show, okay, wait, just want to check. Yeah. So before we get there, let's just summarize again what our ultimate objective is. We have a data set. We have a data set and we have assumed model. That model might be wrong. We need to first check that, or we need to fit the model and check how that model fits the data. But we have data and we have a model with unknown parameters. We would like to infer the distribution over those parameters given the measured data. So since we have limited data, we would like to quantify the uncertainty. We can use Bayesian inference to calculate the posterior distribution over the parameters. So how can we find the posterior distribution? We can again use Bayes' rule in this case. So we're going to use the likelihood function times the prior divided by the model evidence. And now I'm going to just use a very simple example just to explain this process. So let's assume we have a model with only one unknown parameter. Let's say the mean of the model or the temperature in this room. So we have an underlying parameter and we have some noise added to it due to, let's say, sensor noise or measurement noise. So we would like to infer the distribution over that parameter given the data we have measured. So Bayes' rule indicates us if we want to have the distribution over the parameter, given the data we have measured, we need to calculate this function here, the probability distribution over x given theta, which is the likelihood of the model with the given parameter. So that's the likelihood function we calculated previously. We need to multiply it with a distribution over the parameters, but this distribution does not incorporate any data. So this is the distribution over the parameters before we have observed any data. And then we need to divide this over a distribution that's only a function of the data. So this is the process we need to follow. So in this case, I'm going to choose a prior. And the prior is an important selection in Bayesian inference. It's also very application dependent, how you select the prior. I can go in a bit more detail on that at the end. But in this case, I selected a prior distribution. So this is P theta. So this is just a distribution over theta before we have observed anything. Okay, so now we have that. We have that function defined. I can go and calculate the height of this PDF at any theta. So the height of this PDF at -2 is exactly equal to 0. It's 10 minutes. It's uniform distribution. The probability distribution of x given theta, this is the likelihood function we need to calculate. In this case, I just selected a likelihood function just to demonstrate this. I chose a triangle because it's easy to calculate the area of a triangle. So, but it's the same process we followed earlier to get to this function. Okay, so we multiply the heights for each parameter. And let's assume that it looked like this triangle. To get to the numerator of Bayes' rule, we just need to multiply the prior with the likelihood function. So we calculate these products, and we calculate this new distribution here. So the product of this uniform distribution and this distribution here, you can see that the product of this and this would make this region here 0. So this part here is 0. Okay. So this is now the numerator of Bayes' rule. So prior times the likelihood. Now we need to calculate the denominator of Bayes' rule. The denominator of Bayes' rule can be calculated using the joint distribution, which is just the numerator of Bayes' rule. And we can integrate it over all possible parameters. Okay. So intuitively, I demonstrated to you that the numerator of Bayes' rule is the product of the likelihood function times the prior. In this case, it's a triangle. And all that the denominator term is, what's the area under this triangle? That's all that this equation here is indicating to us. So this area under this triangle is this yellow section here, and it's equal to 2. So the Bayesian, our posterior inference, or the posterior distribution, is the product of the likelihood times the prior divided by 2. And that 2 is just because that's the area under the curve. I specifically chose it like that. It's a nice round number. Of course, in practice, would not ever see this again, but this illustrates the process. That term in the denominator is a constant. And this is the posterior distribution. It's just a scaled version of the likelihood function times the prior. Another thing is, because that term in the denominator is just a constant, the posterior distribution is proportional to the numerator, the product of the likelihood and the prior. So if we wanted to calculate the maximum of this, so in using the log likelihood, the maximum, the parameter that corresponds to the maximum value is the maximum likelihood estimate. If we wanted to use the Bayesian equivalent of that, we would use the map, the maximum a posteriori estimate. And in that case, we can use just the numerator of Bayes' rule to calculate that. Those two are proportional to one another, and in this case, it would be equal to 2. The value, the theta that maximizes this is equal to 2. Just want to see now. Okay, and this is the process. I'm just going to quickly skip a few slides. I'm going to skip this model here. I just want to quickly just get back to the linear regression, and then we can, I think then we're out of time. So I'm just going to skip this. So just to illustrate the process, again, I'm going to use a very visual description of this. Because we have two unknown parameters in our linear regression model, we need to have a two-dimensional prior distribution. We will need to have a distribution over those two parameters. And in this case, I chose it to be a multivariate Gaussian. Okay, so it's just, and this is the maximum is there at the center. So it's a zero mean Gaussian. So this is our prior. This is the likelihood function we saw earlier. So the numerator of Bayes' rule, or the log of the numerator, is just the sum of the likelihood plus the prior, the log of the prior. So the numerator of Bayes' rule was the likelihood times the prior. The log of that is the log of the likelihood plus the log of the prior. And this is what I'm showing here. And there we have the map estimate. If we wanted to calculate Bayes' rule, we would have to go and calculate the numerator, not the log of the numerator, and we would have to integrate over all parameters. So the integral over all parameters is just the scalar again. We just need to integrate this map and calculate the integral under that distribution. If we had 10 parameters, we would have to integrate in 10 dimensions, which is the complexity if we wanted to follow this approach in practice. So the posterior distribution then looks like this. It's a scaled representation of that numerator. And then if we sample from this distribution, we get a distribution of models. And these models indicate to us the uncertainty we have because of the limited data. Maybe we don't have time to cover the posterior predictive distribution, but this is the generative model we have. So just to, this may be just the last thing, just to compare the samples from the posterior and the posterior predictive distribution, something that you would hear when you read through the literature, or at least for a textbook. The posterior distribution indicates to us the uncertainty in the model we have due to the limited data. If we have 5 data points, we are very uncertain. If we have 100,000 data points, there's no uncertainty. We only have one line. If we wanted to generate new data from this sample, if we wanted to use this as a generative model for the data we have observed, we would have to use the posterior predictive distribution, which is shown here. It stays the same. It's also affected by the uncertainty, but for all practical purposes, it doesn't shrink like the top distribution does. Okay, so this is the 5 minutes. I went even faster. I should have gone for the previous model also. No, I'm just joking. So just to summarize the process, this was a very visual representation. I think there are enough good resources to learn Bayesian inference, but you need to conceptually understand this. And hopefully this helps you to at least understand the steps that were followed. So this was a grid-based procedure. I brute force evaluated each point. I plotted it. I multiplied it each point by point. I integrated it numerically to illustrate the process. But in practice, we have closed-form solutions available. For the Bayesian linear regression problem, you have equations that give you that. But you need to understand intuitively what those equations mean. And this is what they mean. This is where they come from. Of course, we just have now an elegant solution that's much faster to calculate. But in practice, we don't have always closed-form solutions available. And then we need to use approximate methods. That's where variational inference comes in. Or we need to use sampling methods. That's where methods like Markov chain Monte Carlo comes in. There are, of course, other considerations like prior selections, likelihood-free approaches, etc., that I could not get into. But there are, of course, challenges when applying Bayesian inference in practice. The last thing is just there are very good Python packages. I'm biased towards Python that you can use. Pyro and PyMC3 are probabilistic programming languages that already does the sampling for you. But again, you need to understand the tools that you're using. And this slide is going to show some resources that you might consult. So Bishop is a very good resource, but it's a bit intense if you are not familiar with the material. But the textbook at the top, I think, is very good for non-statisticians, it's for physicists, so it's very intuitive. So if you would like to consult more. Thank you very much. That's the end of my talk.
All right, so technically I think it's 12, so lunch starts now, but maybe we can take 1 or 2 quick questions.
What is the main advantage of Bayesian inference compared to classical inference? What is the main advantage? What can you recommend to convince someone to take Bayesian?
If you're a frequentist, I'd have to tell you it many times. But no, I'm just joking. But so the Bayesian inference it's a nice, for me, it's a nice way to firstly quantify uncertainty. You get it naturally from that. I think, again, it depends on where you're coming from. I'm an engineer. This is intuitive representation for me. The frequentist has a lot of theory and a lot of support for it, but I think, at least for me, the impression is always the sampling distributions you kind of, let's say, solve for afterwards, after you've written down the estimated. You need to use asymptotic properties to get that. The Bayesian is a nice, compact, elegant way to get that. But I think there are very similarities between frequentist and Bayesian approaches, for example. The sampling distributions look very similar to a posterior distribution. But I think the fact that you have the likelihood of a prior, the prior for engineering is very important because we typically have physical models, we have strong assumptions, we have limited data, and we use that to update the prior. It's a nice, elegant way to formalize our assumptions. Instead of adding regularization at the end, we choose a prior with very specific assumptions. It's very transparent and it reflects in our posterior. So, yeah, I think it's a way nicely to encode your assumptions and to naturally recover uncertainties. So that's my thing.
Any more questions?
Your notation where you have lowercase p and then lowercase x in brackets, what exactly do you mean by that? Because if it's a single, if it's an inverted point, then it's 0 if it's a continuous distribution.
So the uppercase is probability. So I use the lowercase for probability distribution. So for the parameters which are continuous, for the data sets that were continuous, I used lowercase p because it's just that height of the PDF. So the probability is undoubtedly 0 of a single point, but the PDF is non-zero. So if we integrated that lowercase p over a specific domain, we would get a probability out. But the probability of observing a specific continuous random variable point is 0. But so the lowercase p was used for probability density functions.
Partial derivatives here.
Yes. Yes, yes, yes.
All right, any last important question? If there are none, thanks, Peter, again.
Okay.
Okay, so next up on our agenda is lunch. Otherwise, you guys will not have yet there, so you want to make your way to the Edwards restaurant, and we'll see you back here at 1 o'clock. I think next up is the keynote, so we all gather in.